Last time we started section 1.1, and we took a look at problem-solving method, I guess. And specifically, we looked at one problem from a gentleman named Gauss, and how he was able to take a problem that looked very tricky and very cumbersome and make it simpler. That was really what he did. And what he did is he changed things so that he could recognize that addition is really just multiplication if you can make a few changes to it. And this was how he added together the numbers from 1 to 100 in that way. And what we're going to look at today is taking a similar, clearly related problem and trying to do the same thing, but kind of seeing where the differences lie between what he did and what we can do now that we change it up a little. So the problem that we're going to look at, instead of going from 1 to 100, is going to go from 36 to 147. Okay, so as everybody understand that the goal is still going to be to do the same thing. It's going to look very much the same way, but there obviously have to be some changes made since we're not starting at 1 and we're not stopping at 100. So one of the things that we did when we looked at this strategy is I wrote out the first three numbers, I put the ... and I put the last three numbers, right? So we're going to start the same way on this one. And we also called it S equals, so I'll do that as well. So S equals, S just standing for sum. There's nothing special about it. And this one doesn't, I talked about what we do, or that sometimes the numbers skip. This one doesn't skip any numbers. So I'm writing out every number. And then I need 145 just because it's not listed, 146, and 147. So with our friend Gauss, what did he do after he wrote sort of the numbers out to begin with? What was the next step we did over here? Yeah, so he wrote the numbers again, but like in reverse order, so that the addition ended up adding the last number and the first number together. Okay, so he decided, okay, well, I'm going to just rewrite it like this. So I've got 147 here, and then 146 and 145. And then I'll put that, dot, and then I've got my 38, my 37, and my 36. And this is still S. So when I end up adding these, sort of numbers together column-wise, vertically, I'm still doubling what I started with, right? Because I'm adding it to itself. So what do I get when I add 36 and 147? 183. And what do I get when I add 36 and 146 together? 183. And when I add 38 and 145 together? 183. And that is the beauty and the whole reason that we're doing that, is because it always boils down to that. I end up with the same number being added together because I've done this reversing and adding vertically pattern. Okay, always works out like that. That's the significance. And of course, the same thing over here. I have 183, 183, and 183. So I have a bunch of 183s, and that is 2 times or double what I started with. So that's why it's 2S. It's just double the sum. But adding the same number together over and over and over again is easier than adding different numbers together, because we have a shortcut for that. That's the beauty of multiplication, right? So I have a daughter, who's in the 5th grade, and she is still struggling with her multiplication facts. And yes, she should have learned them in 3rd grade. And yes, we should have worked a whole lot harder in 4th grade when I knew she didn't. And we tried, time got away from us and it didn't happen. And so we're still working on this. And what I told her this summer when we were working on math is she works so much harder, because every single time she has to do 9 times 8, that's not a good example. We'll do 8 times 7. 8 times 7, she has to add 7 together 8 times, or add 8 together 7 times. And that's a lot of work, isn't it? I don't want to add 7 together 8 times. I mean, really, like, she's got other tricks, like, the 9s trick, right, with her fingers. So I have to hold her hands still so she doesn't do that sometimes, because we're trying to get memorization down. But anyway, the whole point of multiplication is that it makes addition faster. I mean, that's really it. So we know that this is going to turn into a multiplication problem. If you take a look over here at Gauss, we took the number that he was adding together lots of times, which was 101, and we had to figure out how many times he was adding it together, right? And on this one, it was really nice because it was the numbers from 1 to 100, so obviously there were 100 numbers, right? It's not quite that straightforward with this one because it doesn't start with 1. If it started with 1 and ended with 147, how many numbers would there be? 147. Everybody with me so far? But he doesn't have the first how many numbers? 35. The first 35 numbers are not in my list, correct? So the number of numbers, right, how many do I have, is actually 147 minus 35 because there are 35 missing at the beginning. It's not minus 36 because there's the 36 numbers in the list. That's the tendency, is to want to subtract the first number. But it's actually the number that comes before it that we subtract. All right, because that's the one that's missing and everything prior. So if I take 147 minus 35, how many do I have actually? 112 terms. So over here, when I change this into multiplication, I end up with, actually let me do this just to clarify, make sure everybody's good. $112 terms. So when I change this into multiplication, I actually have 183 times 112. And that's actually twice as much as I want because I've added it to itself, right? So eventually I'm going to have to divide by 2 to get rid of those double counts, right? But what is 183 times 112?
20,496.
And then if I divide by 2 to remove my double counts, what will I have?
10,248.
Fantastic. So the values can start wherever they want to start and stop wherever they want to stop. Now let me kind of give you an idea of what would happen if the numbers skipped, right? Like what happens if it's every other number? Like it's only the evens or only the odds. Or what happens if it counts by 5s? What do you do then? Well, you do the same thing. It's just that when you count how many terms you have, you obviously don't have all the terms, right? Some of the terms are missing. They're just not in your list. So let's say for a moment it counted by 3s, okay? So let me just make up sort of an in-between question here just to show you the counting methods for the list. Let's see it counted by 3s. And it didn't start with the first one, so it starts with 12. And then it goes to 15. And then it goes to 18. So we're counting by 3s every time. So every third number is in my list. And we keep going and we end up at the number 312. I'm making these things up as we go, right? What do? Well, you still take the ending number and you subtract what happens that's not there. But what you have to do is you have to figure out what is it that's not here. And in particular, it's always the number that comes before. So what would be the number in this pattern before 12?
9.
It would be 9. It's not 11, right? Because 11's not in the pattern. I know 11 comes before 12, but it's not in the pattern. So the missing number, if you will, is actually a 9 here. So what you would do is you would take the 312 and you'd minus 9. But again, that would count all the numbers, and I don't have all the numbers. I have every third number. So then you'd have to divide by 3. Okay? So it's only in the counting how many numbers. Everything else is the same. I line them all up. I switch the order. I add things together. It's only in the counting of the numbers that things get different and have to be thought of in a different way. Okay, let's try a different problem-solving strategy. We're going to examine a simpler case. So suppose we have a soccer league with 10 teams, and each team plays every other team once. This is pretty typical, right? Like this is real life stuff, like really real life. Like my kids have played soccer before. They do this, right? And the league manager needs to schedule a bunch of games. And the question is, well, how many games does he need to schedule? So there's lots of ways to do this, and I'd like to use this example to show you a way that you can do this to consider a simpler case. You may be able to figure this. You maybe you've scheduled soccer games or something like this before, and you're like, I know the answer. That's great. Wonderful, but what if it's a different problem? So I want to show you a way to use a simpler case to think about it. So let's pretend there are only 3 teams. Lots easier to work with 3 teams than 10 teams. And again, for the sake of not having to be so cumbersome, we're going to call the teams A, B, and C. Okay? So let's see what happens. Well, we have Team A. And Team A has to play Team B. So AB is Team A playing the team. And Team A has to play Team C. And then we have Team B. And Team B has to play Team A. And Team B has to play Team C. And we have Team C. And Team C has to play Team A. And Team C has to play Team B. So I might be tempted to say that there are 6 games. There are not 6 games. Why are there not 6 games? Yeah. When I write AB, that's A and B playing, so I don't need to write BA. Did everybody see that? I actually double counted all the games. Because what I did is I actually went through and I counted all the teams Team A plays, all the games they play, and all the games Team B plays, and all the games that Team C plays. But that's not really how many games they each play in total, right, when you add them together. There's some double counts. So just like I did before, when I talked about these double counts, I can't double count things. So like this one's a double count. And, this one's a double count. And this one's a double count. I don't care which 3 you mark out. But there's 3 that are double counting. So this sort of looked like there were 6 games, but then I removed double counts, so I had to divide by 2, because when I did that, I ended up with twice as many games as really existed. Any idea why I had 6 to start with? If you consider the fact that there are 3 teams. In pairs, right? That's part of it. There's a little bit more though. Yeah. So there's three teams, and they each play 2 games because there's 2 other teams that are available to play. Right? So imagine what would happen if you had 4 teams. If you had 4 teams, how many games will each team play? You'd play 3. Okay? So what's going to happen when I have 10 teams? Right. The 10 teams each play 9 games. But it's not 10 times 9 games, because what would happen if I do that? I would double count everything, right? I counted the game under Team A and I counted the game under Team E, or whatever it is. So I do multiply the 10 times the 9, just like I would multiply 2 times 3 to get 6, but then I have to divide by 2 to remove the double counts. So what is 10 times 9 divided by 2? 45 games. Sometimes it's easier to simplify what you're actually looking at and then generalize it to what happens when things get bigger. All right. Next one is probably one of my favorites. The strategy says make a diagram. Now, when you read this description, that's probably not the first picture or the first thought that comes in your mind. A store sells bicycles and tricycles. There are a total of 15 cycles in the store, and there are 35 wheels on those cycles. How many of each type of cycle are in the store? Now, most of you are not that far removed from an algebra course, and you probably would have done this problem how? What is it? Not with factoring. With what? With X and Y, some kind of an equation, right? In fact, not just an equation, but 2 equations. One equation that talks about the number of cycles, and one equation that talks about the number of wheels, and you would put an X and a Y in there, and you would have used something called systems of equations. And that's totally a legit way to do the problem, but it's really overkill too. This problem can be done by a much younger student if you do it differently. So let me show you how. It told us that there's 15 cycles, correct? And each of my cycles has at least how many wheels?
2.
2. So we're going to draw bicycles. My bicycles are not going to look like bicycles because I don't draw well anyway, so what's the point? So here's my bicycle, just like that. It looks like a cherry, right? Cherries, grapes, something like that. And I need 15 of these guys. So I have this beautiful thing called copy paste, and I'm going to use it. I have 15 bicycles. Do you have 15 bicycle-ish sort of things on your paper? Wonderful. If I really had 15 bicycles, how many wheels would I have? 30. How many wheels am I supposed to have? I'm supposed to have 35. So I'm missing how many wheels? 5. So what am I going to have to do to make up for those 5 wheels?
Take a bicycle and get a tricycle.
Yes, I'm going to take a bicycle and I'm going to put in a tricycle, and my image, what it's going to look like is I'm just going to add another wheel, right? I need to add 5 more wheels. So this is my tricycle. Now, isn't that cool? You were looking at that and thinking systems of equations or something like that. How many bicycles do we have? 10. How many tricycles do we have? 5. And we did it in just, I don't know, maybe 2 minutes. 10 bikes, 5 trikes. So systems of equation type things sometimes work really nicely with a diagram instead of equations. The next question is actually something you probably saw in an algebra course as well. Again, done with higher level strategies, but they can be done in different ways. It talks about fencing something in, making an enclosure. And we are going to draw a diagram to give us some perspective, but we're also going to use guess and check on this one instead of algebra to do it. So it says we have 48 feet of fencing, and we wish to make an enclosure along one side of an existing barn. What lengths would the sides need to be to have the greatest area enclosed for our chickens? So we first have a barn over here. Okay, so this is my barn over here, right? When you build along the side of an existing structure, you fence something in on the side of an existing structure, you never waste the fence by lining the building with the fence, right? So this side is already bounded, so the fence that I create will not have 4 sides. It'll only have 3. Does that make sense to everyone? Mm-hmm. Okay, great. So when I draw my fence in here, it's only going to have 3 sides. Oops, I didn't mean to do it there. Try it over here. And the other thing is that fences are generally not done in random shapes. Rectangles? Yeah. I mean, like, that's just what real life does. Nobody creates circular fences. Man, that'd be tough. I mean, I know sometimes people do a little bit different kinds of enclosures depending on their property. But again, most properties are in rectangular shapes. So we're going to create a fence as a rectangle like this. Imagine it touches my, I'll make it touch, in fact, here. All right, that's closer. So I have a 3-sided fence that I'm working with. So let's go back up to a little of the details of my fence again. It says I have 48 feet of fencing, and it says I want the biggest amount of area inside my fence. So we're going to create possible guesses for the length and width of our fence. So I'll create the first guess. My first guess is that this needs to be a 10. But if the top is a 10, what else do you automatically know?
Bottom is a 10.
The bottom is a 10, right. Opposite sides of a rectangle, they're the same length. Then how many feet of fencing do I have left? 28. So it makes this 28. Okay, so everybody got the idea of how I'm making my choices. And 10 is random. I didn't pick it because of any particular reason. It's the first one on the paper when I created it, however many times ago I did this class. So my first guess is 10, 10, and 28. And when I find the corresponding area that goes with that, how do I find the area when my sides are 10, 10, and 48? I'm sorry, 10, 10, and 28 is what I meant to say. Height times base, or length times width, whatever language it is. And in this case, it would be 10 times 28. I'm not going to use that. I'm going to use a dot. 10 times 28 for a total of 280. And since this is in feet, that would be square feet. Okay, that's my first guess. It might be the right one. But if that's all you do, that is definitely not justification that you have found the right one. You got to try some other things. All right, so we're going to go back over the picture. I'm going to erase my 10 and my 28. And I'd like for somebody else to pick something besides 10 that goes on the top and the bottom.
Can I say, can we just divide the
Just give me a guess.
Okay.
Yeah, just pick me a guess.
12.
12. Okay, so you'd like to do 12 here, which makes 12 here. So how many is left on the third side? What's left? 24? Yeah, 24. Good. So this is another legitimate guess. 12, 12, and 24. And part of what you said divide the 48 by 2, right?
By 3.
By 3?
Yeah, making the 3 sides.
Okay, but then you didn't actually end up dividing by 3. But you got something else close, right? Okay.
Yeah, sure.
The 12 and the 24 are actually closer together than my 10 and my 48, my 10 and my 28 were. So that's one way to think about it. You can also think, well, I'm just going to change the 10 a little bit and see what happens. 10 to 12 is a little bit of a change. Does it get bigger? Does it get smaller? Am I getting further away or closer together? So all of those kinds of ideas would be good. So if we did 12 times 24, what do we get? 288. So is that better?
Yes.
Yeah, for what we want it is. I want the maximum enclosure, so that's a better fence than I had before. But again, is it the best? Well, maybe, maybe not. So let's try again. What else might we try? 16. Okay, 16 here and here. What does that leave for my third side? Is it 16? Okay, so this would be the actual dividing by 3 idea that you had to see if this would be give me a better choice. So 16, 16, and 16. And what is 16 times 16? Ooh, so this one didn't quite give us as much. Now here's something interesting to notice. Both 10 and 16, one smaller, one larger than 12, gave me smaller values than the 12 did, right? So it's a pretty good idea to guess that maybe if I go further away from 12 or something nearby 12, I'm getting smaller values. But is it really 12? Or is it maybe 13 or 14 or 11? And the only way to check, well, it's not the only way, but when we're working with this, what we would want to do then is to check and see if any of those numbers are giving me better solutions. So which one would you like to check next? 11? Okay, let's try 11. So 11 and 11 leaves me with what? 20 what? 6? Okay, so 11, 11, and 26. And I would multiply 11 times 26. And what would that give me? 286. Better or worse? Slightly worse. But man, it's really close, right? It is really close, but still 12 is better. But is 12 the best, or is there, so, I mean, we've tried 10, 11, 12, and it's gotten better each time. So maybe if we go from 12 to 13, it'll get even better, right? So let's check and see. So if I do 13 and 13, how much am I left with? 22. Okay, so I have 13, 13, 22. 13 times 22, and what does that give me? 286. So when I was at 12, I was at 288, and when I went slightly smaller than 12, I was at 11. Slightly bigger than 12 at 13, I both of those directions actually gave me smaller values, right? So at this point, we've done enough guessing and checking with the right combination of things, right? We're not randomly guessing and checking. We start out that way, but we have to keep a list and make it organized in such a way that we can eventually figure out, where am I getting with all my guesses? And we've done that. We know the answer to the question. Now we have to make sure we answer it. The question actually asked, what lengths would the sides need to be to have the greatest area enclosed for our chickens? So what lengths would the sides need to be?
12, 24.
Okay, so they would need to be 12 feet, 12 feet, and 24 feet. Now, they could have equivalently asked us what's the biggest area that we've enclosed, right? So be really careful. Those are asking different questions, but obviously from the same pieces of information. We just need to make sure we answer the question that's asked. Any questions on this one? Again, have you done problems like this before with some algebra and some equations? Yep, you probably have anyway. Yeah, usually. All right, let's take a look at a different one. We talked about the strategy of working backwards last time and about how, I know you've done it before because we've all looked at the back of the book and said, how did they get that answer? And they've tried to work backwards to get to the point where you had the question. So here's an example of a problem that working backwards actually is a great strategy. It says, one winter night, the temperature fell by 15 degrees between midnight and 5 a.m. By 9 a.m., the temperature's numerical value had doubled from what it was at 5 a.m. By noon, it had risen another 10 degrees to 32 degrees. It would have to be Fahrenheit. What is the temperature at midnight? So part of what we need to do is to write down sort of a detailed list of what the information they're giving us, right? There's some different time frames. What's the earliest time frame that they give us?
Midnight.
It's midnight. What happens after midnight? Sorry, I didn't ask the question right. What's the next time that's listed after midnight? That's what I actually wanted to ask. 5 a.m. Okay, 5 a.m. What's the next time that's listed?
9 a.m.
9 a.m. And then
Noon.
Okay, good. Thank you. And what we're wanting to do now is to figure out what happens between it. So you're about to tell me what happens from midnight after till 5 a.m. What happens between these?
Okay, it falls by 15.
It falls 15. And what happens between 5 and 9? It doubles. And what happens between 9 and noon?
Rises 10.
It rises 10. And then there's one more bit of information that's like the kicker at the end, and it is that it is 32 degrees down here at the bottom. Okay? Oops. You write it like this. Let's go like that. Okay, 32 degrees. So we're going to go from 32 degrees back up my list. So we know that it rises 10 degrees to be 32 degrees. So what was it before it did that? 22. So going back upward, it was 22. We knew it doubled from 22 to get to 22. So what was it before it doubled? 11. And we know it fell 15 degrees before it was 11. So it was before this, or what was it before this?
26.
26. And our answer is that it was 26 degrees at midnight. Any questions on that one? All right, when we break apart here in a minute to do your group work, you're going to see one interesting question at the end of the group work, problem number 10. It's going to talk about the 12 days of Christmas. And so I wanted to use this opportunity to tell you a couple of things about this 12 days of Christmas. It's very interesting. So you've probably heard the 12 days of Christmas before. And if you're anything like me, once you get up past about 7 or 8, you lose track of which of those creatures came next. And in fact, I've had books, children's books, that screw it all up, and then it really plays with my mind. And then I really can't remember which one comes next. So part of this slide these two slides have to do with helping you to know which one actually comes next, because it'll help you with the problem. But it's also because there's actually some religious symbolism behind the 12 Days of Christmas song. It's not just a cutesy little song for children. So I'm going to show you the 12 Days of Christmas symbolism. So the first day of Christmas, it talks about the partridge in a pear tree, and it talks about my true love. The true love is God. On the second day of Christmas, you got 2 turtle doves, and the 2 turtle doves represent the Old and the New Testament. The 3 French hens represent faith, hope, and love from 1 Corinthians 13. The 4 calling birds represent the 4 Gospels. What are they? Very good. Matthew, Mark, Luke, and John. You guys as Old and New Testament professors would be proud, especially the New Testament one. Okay. 5 golden rings is the Pentateuch. Do you know what Pentateuch means? The first 5 books of the Bible. Can anybody name them? And Numbers, right. And a little bit, Numbers and then Deuteronomy. But you got them. Yeah, I heard you. Some of you fell off the mark at Leviticus. So, yes. Yeah. But, so Genesis through Genesis, Exodus, Leviticus, Numbers, and Deuteronomy. Very good. The 6 geese a-laying are the 6 days of creation. I won't make you label them all, but you know God made it all, right? All the way from the stars and the moon and the light and all that good stuff down to us. That's right. The 7 swans a swimming are the 7 gifts of the Holy Spirit. Oh, where's my other slide? Oh, wait, there it was. I just went on too far. My 8 maids a milking are the 8 Beatitudes. You know, blessed are the meek and, poor in spirit, all those. Those are the Beatitudes. The 9 ladies dancing are the 9 fruits of the Spirit. Do you guys know any of them? Love, peace, patience, kindness. Oh, you guys are fantastic. Yep, all of those. Yes, my son just chose that as his verse to share when he got baptized, actually. It was the fruits of the Holy Spirit one, yeah. The 10 Lords of Leaping are the 10 Commandments. I might have referenced those the other day when the same son was lying to me. The 11 pipers piping are the 11 faithful apostles. So who gets left out? Judas. Yes, he would not be a faithful apostle. And then the 12 drummers drumming are the 12 points of the doctrine of the Apostles' Creed. And you've probably heard a song that has the Apostles' Creed in it. It says, I believe in the Holy Spirit, one holy church. I'm not going to sing it because that would be bad. But there's a song that actually listened, and it's a fairly contemporary song in the last, decade or so anyway, and I'm sure that you've heard it before. So here's one more thing to make you aware of, because sometimes people think about this incorrectly when we get to the actual mathematical problem about it. So on the 5th day of Christmas, you get the 5 golden rings, but you also get 4 calling birds and 3 French hens and 2 turtle doves and the partridge in a pear tree. Okay? So you get all of those gifts again. So you don't just get the 2 turtle doves on the 2nd day. You get them on the 2nd day and the 3rd day and the 4th day and every day thereafter. Does that make sense? Wonderful. All right. So we're going to separate into groups. I'll pause this here in just a minute. Once we've separated into groups, this person will be your group work partner for all of chapters 1 and 2. And then you will get a new partner once we get into the next unit, which is chapter 3. Basically, I'm going to assign you based on where you're sitting. But a couple other things to be aware of. At the very end of this lesson, it tells you group work, homework, right? So as a reminder, we're going to do the group work in class. If for some reason you don't complete it, you just finish it up on your own. And then on the same piece of paper or on another piece of paper stapled to it, you're going to continue with the homework. When you come to class on Wednesday, you're going to turn the group work and the homework all in as one assignment. Sound good? Okay, now let's talk about the ABC. Some of you have actual textbooks. Most of you probably have the electronic textbooks. So I do hope that you have your phone or computer or iPad or something that will access this between you and your partner. If one of you could, that'd be awesome because you're going to need it. Also, it says ABC. Section A problems have all of the answers in the back of the book, whether it's electronic or not. You'll be able to go back there, check your answer, make sure you're on target, okay? So I'd encourage you to check as you're going along and making sure you're not making mistakes along the way. Section B, none of those are in the back of the book. But Section B number 5 is very similar to Section A number 5. So again, if you go look at Section A number 5 and can see what's happening with the back of the book, that might be of help to you. Section C, sometimes they're in the back, sometimes they're not. Also, Section C does not say section C. It says communications or connections or something like that. Some word that starts with C, and C follows A and B very nicely, so I call it section C. Okay?